Okay, this is the second hour of Physics 1B for October 11th, and we were looking at this problem right here. Were you all able to solve it, and does anyone have a method they want to share with us about how we do this? What do we do? Given all this information about the size of the scuba tank, etc., how do we figure out how much air, the what is it, the mass of air that was added? How do we do that? Solve for n, and then can and solve for n for what? Like, let's see here. We have delta n, the change in n, finding the number of moles. Again, these all sound like great strategies. So there's going to be a kind of starting number of moles, and then after we've pumped in the air, we'll have a number of moles that we'll call number 2. So this one's going to be equal to something like, well, we have the equation. Let's just write it down right here. PV equal to nRT, which means that N is going to be equal to PV over RT. So this is going to be like pressure 1, volume 1 divided by R times T1, and then this one will be pressure 2 times volume 2 divided by R times T2, and then we can just write down what we have. We know that the scuba tank has a volume, which we'll call V1, that's equal to 11 liters. I don't think the volume changes, so this is also going to be equal to V2. The air has a temperature, T1, that's 21 degrees Celsius, which we add 273 to that. We'll get 294. What's T2? It tells us that the air temperature is then 42 degrees Celsius, so this is going to be 273 plus 42. So that's going to be 315. And then, so the other thing we need is pressure. Okay, so the initial pressure was 1 atmosphere. And then P2, it says that the gauge pressure is 2.1 times 10 to the 7 pascals. So if we want to get the actual pressure, what do we need to do with this? We have to add something, right? So if we have the gauge pressure, how do we get the absolute pressure? Yeah, we have to add 1 atmosphere. So 1 atmosphere of pressure would be 1.013 times 10 to the 5th pascals. It's not really going to change this number by very much. It's just going to change that 1 digit right there, basically, right? Okay, so in this problem, there is some kind of like mixture of units that we've been given, right? So we got to be a little bit careful about how we do the calculations. So we can't just instantly plug the numbers in. Pressure 1, if we write it as 1 atmosphere, which is fine, then we better write volume in what, liters or meters cubed? It's going to be liters, right? And then we need to use the version of R that's 0.080402. What is it? I don't know. I don't use this one for 0.08206. That's what it is. 0.08206. And that's the, what's the unit? This is liters times atmospheres per mole Kelvin. Okay, and then we just multiply by the temperature, which was 294. You know, I guess we could have done all of this as one big equation, couldn't we have? Oh well. So this is going to give us a value for N1, and then over here we have N2. For N2, pressure 2 is in pascals. I think this is going to be 2.11 times 10 to the 7. Right? If that's wrong, tell me if that's wrong, but I think that's right. And then if we write it in pascals, we now have to write volume in meters cubed, but I think you just divide by 1,000. So then we multiply this by 1 meters cubed And then in the denominator down here, we're going to have 8.31 joules per mole Kelvin times pressure, temperature 2, which was 315. I'm going to kind of assume that some of you have probably already calculated this. So if you have values, can you write like N1 equals, N2 equals in the chat? And then I'll just put them in this calculator. Let's make this smaller so I can actually like see the thing here. Okay, see people are typing. Okay, so this one would be here, 11 divided by 294. That's N1, and then N2 would be 2.11 E7 times 0.011 divided by 0.31 divided by 315. 88.6. Looks like that's the same thing that Astrolover just put in the chat, so that's good. 456 and 86 point... 88 point... Here. 0.0456. That's moles. And the other one's... I got 88.7. We're going to write 88.7. Our goal was to figure out the mass of the air added, and so the original thing that Christian was saying is we need to find delta N. So that would be N2 minus N1. And then if you know the number of moles and you want to find the mass, you need to, what, divide by molar mass? Nope. Multiply by molar mass, right? Because molar mass is the number of grams per mole times moles would give you grams, right? Okay, so if we do that, then we'll have 88.7 minus... Am I supposed to put an S on the end of mole? Or is it just mole? I think it's just mole, right? Maybe it doesn't matter. And then you multiply by big M. So it said here that there's all this extra information. Air is about 78% nitrogen, 21% oxygen, and 1% miscellaneous. And its average molar mass is 28.8 grams per mole. So we multiply by 28.8 gram per mole. And we'll get an answer in grams. This will be the mass. Okay, so we do that minus that times 28.8, 2540 grams. I would guess that if you took these numbers like 78% nitrogen, if you take 0.78 times the molar mass of nitrogen plus 0.21 times the molar mass of oxygen, you'll probably get something like this. Probably. I don't know. Okay, that's, again, just another exercise to get comfortable with using the ideal gas law. Did anyone have any questions? If we try combining it with the volume, not cancel out. Not in this case, I don't think, because because the volume is directly related to how many moles we have here. I don't think the volume would cancel out. You could factor it out, but we couldn't cancel it out. All right, so now we want to do this one. This is a problem that kind of, I guess it's less of a problem, more of like something to think about in terms of how pressure works. So we're trying to figure out in this problem the variation of atmospheric pressure with elevation in the Earth's atmosphere. And we're going to assume that at all elevations the temperature is 0 degrees Celsius, and that the acceleration due to gravity is given by that, you know. And I put these two equations in here. This one that we derived earlier that relates the density of a substance to pressure times molar mass divided by R times T. And this equation is something that I think this is from the very first day of 1B, where we talk about the variation of pressure with depth. If you don't remember this equation, it's usually written in a different way. Let's see. It's usually written like this. dP is equal to negative rho g dy. We used this when we did a problem where there was like a dam, and we had to like sum up all the forces on the dam, so we had to use this equation. But the other way that this is written, as you all know, that if you integrate this, what you end up getting if you integrate dP is delta P, change in pressure, and this is equal to negative rho g times delta y, but delta y is often referred to as just h. So you can imagine if you integrate this from 0 to h, you would get this. And what this says is that P minus P naught is equal to negative rho gh, or that P naught plus rho gh. Add them both. How do I do? Wait. That extra negative sign is confusing me. Let's just multiply it over here. So you get P naught minus P equals rho gh. And then subtract this one, add this one. So you get P naught minus rho gh is equal to P. Well, I was trying to say that this is like the variation of pressure with depth, but the extra negative sign here is confusing me. Maybe I had to integrate from h to 0 so that it became plus. That would have worked for sure. Something like that. I don't know. Point is that that's what that equation is. It's basically just the fact that pressure increases as you go farther down due to gravity. All right, this is an aside right there. I think I probably confused you more than else. But so our goal here is to find how the pressure in the atmosphere varies with elevation, and we're going to basically want to use these two equations to get pressure as a function of height, basically. That's kind of what we're trying to do. Pressure as a function of height. Okay. So we have these two equations. Let's write them down. Rho equal to and this equation here okay, so what we're going to do is we're just going to take this row and we're going to plug it into here. So we'll get dP dy is equal to pressure times molar mass over R times T, and there's a G, and then there's a negative sign. The next thing we're going to do is we're going to say there's a pressure right here, and there's also a pressure right here in this dP. So we're going to divide the pressure down to here and multiply dy to the right-hand side. Let me know if I drop anything here as I'm going through this. It's very easy to do so. I think it's okay. You'll see what we did. We started off with these two equations. We took density, we plugged it into our variation of pressure with depth equation. And then I took the pressure here and put it together with the other pressure. And then what we're going to do now is we want to get pressure as a function of height, so we're going to integrate both sides. So we're going to go integrate this, and we're going to integrate this. And when we do this, we're going to need some limits. So the limits that I'm going to use here are going to be from initial pressure up to some pressure that I'm going to call P prime, just as a kind of dummy variable. And on the right here, we'll go from, do we want to go from 0 to y? I'm not sure. To begin with, we'll go from y initial to y. And then maybe we'll change this to 0 later on if we need to. I think this is fine though, like this. Okay, everyone following along? What are we doing here? And let's think about this for a second. What we're really doing is we're solving this equation. And this type of equation has a name. What kind of equation is this? This is like a preview of mathematics that some of you may have seen, some of you may not have seen. I think it's something that usually comes up at least in the end of Calculus 2. Like the topic is at least brought up. And you may solve an equation like this. You've taken Calc 2 before you come to this class, right? I always forget. Yeah, so this is called a differential equation. And you'll see them show up a lot in physics. You probably maybe first saw this in discussing the way that the acceleration due to gravity varies in free fall due to drag. The other place you may have seen it is in simple harmonic motion. Co-requisite, thanks Noah. That sounds about right. So you're taking it at the same time, basically. But that's being changed, though, soon. Okay, so this is what we call a separable differential equation, where you can take the two pieces of this and you can separate them out. And that's why we multiplied dy from here over to there. And it showed up, as you can see right here. And we were able to basically just take the variables and get all the variables we wanted on one side until we get to here. And then we can integrate, and that's going to allow us to find how pressure varies as a function. Well, to find this function, basically. Okay, so let's continue to do this. What am I going to get on the left-hand side of the equation here? If I integrate dp over p, what do I get? Natural log, that's right. Just scroll down just a little bit here. All right, so this one is going to be the natural log of p prime over p naught. Plugging in limits. Is that okay with you all if I skip that step? That's easy to see what's going on there, right? Maybe it's not. Maybe I shouldn't. Maybe I shouldn't skip that step. There's no reason to. There's no reason to. All right. So what do we do here? This is going to be the natural log of p, evaluated between p initial and p prime. On the right-hand side, this integral is really easy to do because mass, gravity, r, and t aren't going to vary appreciably. It says find the variation of atmospheric pressure with elevation in the Earth's atmosphere. So gravity does vary as a function of y, but the variation is extremely small within the atmosphere because the atmosphere only goes like 30 kilometers up, and within that like tiny height, the gravity is not going to change enough to change. So temperature shouldn't change because we're assuming the temperature is constant, and the molar mass of the this shouldn't change either. There's no reason it would change. Okay, so we can pull everything out of this side, so we just have negative mg over rt. And then that would be times y. And I should have used a dummy variable for this one too. We're just gonna, this is just so that this variable is the same as the variable that we're using here. So we evaluate that between y initial and y prime. And now let's go from here up to here for the next line. So we'll have, over here we have natural log of p prime minus the natural log of p naught equals just negative mg over rt times y prime minus y initial. And then we can use the property of logs that if you have a difference of logs, that's the same as this ratio like this. Our goal here is going to be to get this y prime thing. Oh no, we're trying to isolate pressure because our goal was to find basically pressure as a function of y. So we're going to be isolating this variable. So I guess I just rewrite this down here. Okay, now I'm going to get rid of the primes because we don't really need them anymore. The whole point of them was just so that the variable of integration wasn't in the limit, but at the end of the day, we're trying to find pressure as a function, so we're looking for this p here. Basically, this is what we need to solve for. In fact, we can actually write in here now that... I'm not going to write it yet. Okay, next thing to do... What's the next thing to do? We want to eliminate this log function. How do you eliminate a log function? Yeah, you raise both powers to the e. So we basically go like that. And then e to the log of this is equal to this. It's equal to the ratio of p over p naught. That's all going to be equal to e to the negative my over rt. So all this stuff is in the exponent up here. Y minus y naught. And then we multiply p initial over to here. So you get p initial is equal to p equals p initial e to the negative whoops, I got sloppy there. That's a g. It's a g mg over rt times y minus y initial. And there we go. It's not incredibly pretty, but this is the pressure as a function of height above the Earth's surface. And if you define the initial height to be 0, so if we let y initial be equal to 0, that would be the surface of the Earth, basically, would be, if you call that 0, then the pressure as a function of y becomes p initial e to the negative just mgy over rt. And there we go. So we can even plot this. Okay, all that stuff's still on the screen, right? So if we take this one, and we plot on the y-axis pressure, and we plot on the on the x-axis y, because this is so p is a function of y, so you'd have to write it like that. Then what would this look like? It would look like a exponentially decaying curve like this, saying that as we get higher and higher up in the atmosphere, the pressure gets lower and lower, and it kind of follows this function like this. So why would you care about that? I don't know. I mean, it's nice to be able to have a way to evaluate what the pressure is going to be in a kind of granular way, right? Where you know what it's going to be at like each individual point, because maybe you can use that to model other things, or maybe you need to know this to model how the density changes, for example. Okay, anyone have any questions? Yeah, you can actually, right? You could get the density as a function of height too, right? Because if you know that if you know the pressure is a function of height, and the density is just this, basically m over rt is all that stuff's constants, right? So you could get density as a function of height out of this as well. So that's kind of powerful, which again might be something you need to know when designing, hot air balloons or maybe airplanes. I don't really know. Okay, anyone have any questions? Did I put everyone to sleep effectively with all this math here? I will say you're gonna see this a lot. This same, like, very similar derivations with different systems. Like in 1C, for example, you go through a similar derivation like this for what's called an RC circuit, where you have a resistor and a capacitor. And then you do the same thing for what's called an LR circuit, which is an inductor and a resistor. And as I mentioned earlier, like, if you want to look at how the acceleration due to gravity changes due to, or that's the wrong thing to say, sorry. If you want to see how the velocity of someone's that's falling through the air varies based on time, it's a very similar equation. So it's also a very similar equation that shows up for evaluating the price of a investment over time. Similar equation shows up as well. So I think it's also one with half-life for the amount of substance when you have nuclear material. So it's something that's important to understand, like, how the process itself, because I think some teachers, like, I don't know, I have given questions on tests like this, I guess, where I kind of ask people to redo this derivation, basically. Not necessarily, like, specifically saying it, but there'll be a problem where, like, the way that a certain variable changes forces you to go through this derivation, basically, to solve, if that makes any sense. So it's an important kind of thing to know how to do. So I'm saying I do it. I think other teachers do it too. So it's something to... it's good to know how to go through this process. And the process, again, is you start from an equation where you have, like, so here we have dp dy, right? And over on the right-hand side of the equation, you have p. So we call this separable because it's very easy to get the p and this other p together, which allows you to do an integral, right? And imagine if, for example, there was a y over here. You know, maybe there was like a y squared term here, for example. Well, then you could get the dy with the y squared, right? And then you could do it, basically, you can separate so that you have a y integral on one side and a p integral on the other side, right? And this could be things where, like, maybe sometimes it's velocity and it's acceleration, or maybe sometimes it's like position and force or something like this. Like, just different things can have the same type of relationship. The times when you can't separate them are when you have a second derivative. Because if I have a second derivative right here, right, like if it was... Do you see what I'm saying? Do you all see what I'm saying? Like if this was a 2 and this was a 2, if it's a second derivative, I can't do what I just did, right? I can't separate the dy2 from the... Because this is like two different derivatives, right? So there's no way to do it. But being able to solve this special kind right here, this, as I said, it's called a separable, is important to know because it's the easiest type, and like I say, professors like to hide them on tests. If that makes any sense. So we have, what, about 30 minutes left. Oh boy. Okay, let's see if we can do this in 30 minutes. We might be able to. I don't know. Okay. So what we're going to do now, I think this is really kind of cool, this next thing we're going to do, but after doing what we just did, I didn't think we would get to this today. We got through things so much quicker than usual, which is really good, because we need to kind of keep up the pace. So what we're going to talk about now is called the kinetic... is it kinetic theory? Let me get the right name of it here. No, kinetic molecular model, okay. Okay, the kinetic molecular model of an ideal gas. Okay, what is meant by this? What's meant by this is we just got a macroscopic description. So I want you to think about macro versus micro. Okay, so macro is the big stuff, like the whole collection of molecules. And for those kind of things, we have macroscopic variables. Those are pressure, volume, temperature, number of moles, okay?
that tells us how the total gas behaves, okay, on average, really. What we want to talk about now is the molecular model. That is to say, how do the individual molecules behave for the ideal gas, okay? How fast are they going? What are their average velocities? And how do those velocities relate to the energy of the gas and the temperature of the gas? Okay, so that's the goal. We want to be able to talk about the kinetic energy per atom. We want to know how much kinetic energy does each individual atom have, which means we also want to know what the velocity of individual atoms are. And maybe that's obviously something that you want to study, but I mean, maybe it's not obvious, but we'd like to know just how fast these molecules are going, and we'd like to know what that means in certain scenarios. What effects does it have on, for example, one of the questions we can answer with this is, what type of molecules do we expect to show up on different planets? Okay, that's one of the kind of things that comes out of this is, if we know how fast things are moving, we can know what percentage of the molecules actually can reach escape velocity, and if they can all reach escape velocity, they'll just boil off the planet. Okay, so in order to understand that, we need to know how fast molecules of a hydrogen gas are moving at like 100 degrees Kelvin, right? Or how fast the molecules of a helium gas is moving at 600 degrees Kelvin or 6,000 degrees Kelvin, or whatever we're interested in. And so that's what the goal here is to basically find the velocities of molecules and understand their energies and how it relates to the overall macroscopic variables of temperature. So we're going to make some assumptions, okay? These are the assumptions, and I'll give you, these pictures will pull up here too. Maybe that's too much to look at. Let's just look at these words for now. Okay, so here's our assumptions. Our discussion of the kinetic molecular model has several steps. You may need to go over them several times. Don't get discouraged. I don't know if you need to go over them several times. You just need to understand the results that we get out of this. All right, so a container with volume V contains a very large number N of identical molecules, each with mass M. So this is our first, it's an assumption, but I think this is a pretty safe assumption that that each molecule has the same mass. That's not too drastic of a thing to say, is it? I don't know how you think about things. I guess a molecule basically is, defined as kind of the smallest amount of the substance that you can have without breaking it down into atoms. Whether you believe that's true or not, maybe you believe that some molecules are different from other molecules. I could see why someone would believe that for sure. You've never touched a molecule, you've never felt a molecule. How do you know that they're all the same without taking my word for it and taking the word for it of a lot of other scientists that have figured these things out? So I guess you have to just kind of trust us that all molecules have the same mass. We're going to use the number capital N to represent the number of molecules. We use capital N to distinguish it from little n, which we use for moles, right? And then the volume of the container is going to be V. We're going to assume that the molecules behave as point particles that are small compared to the size of the container and to the average distance between the molecules. That is to say that the size of the molecules isn't going to affect like how the molecules interact with each other. And the size of the molecules will be small compared to the size, which means that the size of the container can't change just because we have to pack more molecules inside and they're far apart. We're going to assume they're in constant motion, and we're going to assume that each molecule collides occasionally with the wall of the container, and that these collisions are perfectly elastic. If you remember that from Physics 1A, an elastic collision, a perfectly elastic collision is one. I don't think you need to use the word perfectly, do you? You could just say elastic, because we said that elastic collisions are ones that no energy is lost, right? We're also going to assume that the container walls are rigid and infinitely massive and do not move. Okay, so we've got a container. It's a closed container. It contains gas molecules. The gas molecules are really far apart, but they're constantly moving. Every single one of them at any moment in time has a velocity. Sometimes these molecules can hit the walls and bounce off, and that will impart some kind of energy to the walls. However, the walls are rigid and infinitely massive, so they're not going to be affected. Like, the walls can't break because of these collisions. And the volume is V. The number of molecules is capital N. And each molecule individually has a mass M. Okay? All right. So what we're going to do now is we're going to imagine what happens for one of these collisions. And we'll talk about how many of these collisions happen per second. And our goal is basically, our first goal is to go from velocity to pressure is the first thing that we're going to want to do. So imagine that we have a molecule that is moving in this direction here, as shown. So we have a molecule that's moving in that direction. This is its velocity before it hits the wall. So here's the wall. This velocity has a component v1y that we're calling vy, and it has a component v1x that's pointing towards the wall, which is called negative vx here. So it comes in, it hits the wall, and then when it goes out, we're assuming that the collision is going to be perfectly elastic, which means that the velocities can change direction, but they can't change size. So vy stays the same before and after the collision, and vx goes from this direction to that direction. So we can say that the change in momentum, so here I'm just going to write, this is change in momentum, would be equal to delta. So I'm gonna try to write this p with this long line right here to represent momentum. In this case, this would be equal to final momentum, which is m times vx, minus initial momentum, which is negative mbx. Okay. So we end up getting positive 2, right? 2 times m times vx. And this is the absolute value, so I guess I should write it like that just to be clear. All right, that's the change in momentum. Does this look familiar to you from Physics 1A? Has it been so long that you forgot momentum? Possibly. Momentum is mass times velocity. Y'all remember that? You probably do. Maybe. All right, so that's the change in momentum, right? Now, the next thing we want to talk about, this is for one molecule. Now, just to keep you on track of what we're kind of the overall goal here is, if this molecule comes in and it collides off the wall, that's going to exert a force on the wall, right? And we know that pressure is force over area, right? So if we have the change in momentum, we just need to know how long it was in contact with the wall, and we can figure out the force. So this is how we get from velocity to force, which allows us to get to pressure. That's kind of the overall goal still where we're going here. Now, in order to do that, since this is the change in momentum for a single molecule, what we need to know is how frequently does such a collision occur, right? Does it happen 3 times a second? Does it happen 50 times a second? Does it happen trillions of times a second? We need to know how frequently this happens, right? So in order to do that, let's imagine that here's our wall, okay? And we draw a cylinder here. Draw a cylinder. And we imagine that inside of that cylinder, we have all of these little molecules, which are represented by the black dots right here. And that those molecules are moving with a speed that we call Vx. We're going to assume that all the molecules have the same magnitude Vx of their x velocity for this kind of thought experiment that we're doing. We're assuming that all the molecules have the same x velocity. Now, in order for a molecule, I'm just going to read what it says right here because it explains exactly what it's supposed to be. For a molecule to strike the wall in an area A during a time interval dt, the molecule must be headed for the wall and be within the shaded cylinder of length Vx dt at the beginning of the interval. At the beginning of the interval. That is to say that if the length of this box is Vx dt, the area of this box is Vx dt, we could say that the volume, so capital V for volume, should be equal to the area multiplied by Vx multiplied by dt. Okay. The point is that you can choose arbitrarily any time interval that you want to. You could choose 10 microseconds. You could choose 1 nanosecond. You could choose 50 minutes, whatever you want to choose. Within that amount of time that we call dt, right? If I take the velocity of the molecules Vx that are in that area, and I multiply by Vx times dt, then I get the length of how far they could possibly travel in that time, right? So if, just to give you an example, if the velocity of the molecules was 1 mile per hour, and the interval of time that we used here was half an hour, then the largest distance that something traveling 1 mile an hour could travel in half a mile an hour, the largest distance that something traveling 1 mile an hour could get in half an hour would be half a mile, right? If it was 2 hours, it would be 2 miles, right? So if you take Vx, you multiply the time interval, that's going to give you the distance. And this is going to allow you to basically get a volume of molecules that all have this same velocity, and they're all heading towards the wall. Okay? Does that make sense to you all? You all still on board here? Okay. So now we have to think how many molecules in our system are actually going to hit. Okay? And one thing that we know is that I'll just write it like this. The number of molecules per unit volume, this is like, it's not density exactly, but it's like kind of like density. We know that this is going to be a constant. Okay. We know that this is going to be a constant. So if we take this and we multiply by volume, it should give us the number of molecules, right? Basically. So if we take N over V and we multiply by this quantity, which is the volume, this should give me the actual number of molecules that are going to collide with the wall during this time. Okay? So this would be the number of molecules N. I'll just write it as number of molecules that collide with the wall in time dt. So we went from the distance that they could travel to the volume that they occupy, and then because we know that the number of molecules per unit volume is constant, if we know the volume that they occupy, we can multiply that to find the total number of molecules that actually collide in time dt. So if it's an hour, maybe it's a trillion. If it's 2 minutes, maybe it's only like a million. Anyway, so this is going to give us the number of molecules that collide with the wall in time dt. However, one thing that we left out was that we're only talking about molecules with an absolute magnitude of Vx. So that means to say that some of them can have a velocity of plus 1 mile an hour, and some of them can have a velocity of negative 1 mile an hour. So only half of the molecules are actually moving to the left. Half of the molecules will be moving to the right within this volume. Right? Does that make sense? They're actually not moving only left or right, by the way. You guys understand that? This just is the x velocity of the molecule. This could be the velocity, but this is just the x component of the velocity. But some of the molecules are actually going to be moving this way, right? So if some of the molecules are moving that way and some of the molecules are moving the other way, and we assume it's a perfectly random distribution, then what we would assume is you really just have to divide this by 2. Because half of the molecules in the volume are going to have an x component that's this way, and half the molecules are going to have an x component that's this way, and you can only have left or right for x component, right? It can't be angled. So that will be the number of molecules that will collide with the wall in a time dt. Okay. So if I want to find the change in momentum total, that if I take every single molecule, right? Every single molecule, we know that the change in momentum for one molecule is this. If I take this quantity here and I multiply by momentum, then I can figure out the change in x momentum. Whoops, not using the right. So I'm going to do dpx should be equal to, we take the number of molecules, so we'll just copy paste this down. Copy paste. That's the number of molecules in the volume. We multiply by the change in momentum per molecule, right? And then we take the dt and move it to the left-hand side. Scroll down just a little bit. And now we're going to get the rate at which the momentum change is occurring. What else can we do here? We can actually group some things now. The 2 and the 2 cancel. The Vx and the Vx become Vx squared. That's right. This one still should have had the bars, I guess, shouldn't it? Okay. Vx times Vx becomes Vx squared. So what do we have? We have an N times A mass Vx squared. And now I'm going to remove the bars because if it's squared, it doesn't matter if it's absolute value or not anymore. That's everything in the numerator, right? And then divided by volume. Let's check. There's an N, a V, an A. Mass, Vx, Vx. The 2's canceled. So there we go. So now we get, so we went from the number of molecules that collide with the wall multiplied by the momentum change per molecule that's going to occur. And if you know the change in momentum of the molecule, then, which is this, dp, then if you find the change in momentum per second, what does that give you? Do you all remember? How are we doing on time? What do you get if you get the... I could ask this a lot of different ways. This is the derivative. So impulse is actually just change in momentum. It's the same thing. But if you're thinking about the right equation, what is dp dt? What's the time rate of change of momentum? Does anyone remember? What is the time rate of change of momentum? If you take position, you take the derivative of position, you get, what do you get? Velocity, right? You take the derivative of velocity with respect to time, you get acceleration, right? What do you get if you take the derivative of momentum, though? What happens if you work out the units? Look at the units. What do you get? The units in the numerator would be kilograms times meter per second, right? Yeah, mv over t is ma. There you go. Force. This is going to give you the force exerted on the wall during that little time interval, dt, of all those molecules colliding with the wall. Now we have force, right? That's great, because if we have force, then we can write that force over area, right? Divide the area here, which we know is also equal to what? That's pressure, right? Now we have big capital P pressure. The pressure then is going to be, what do we have? Just N mvx over v, yeah. So this is going to be N. Oh, we have mass over volume. Do we want to write that as density? I guess we could. No, we can't do that. I want to be very, very clear, by the way. This is the mass of a molecule now. I almost made a mistake there. I was gonna say mass over volume, that's just density. But we can't do that, right? Because it's the mass of a single molecule. That would be a very small density that we would come up with there for sure. Okay, so NA, we got the A, so it's just NMVX whole squared over volume. So this is our first, like, direct relationship, okay, between a microscopic variable, such as the velocity, this is the velocity of one atom, basically, is related to the pressure here. The faster the speed, the bigger the pressure. Does that seem reasonable? Is it reasonable to say that the faster something moves, the bigger the pressure would be? Yeah, it's totally reasonable, right? Not a surprising result, but we didn't know exactly how. We didn't know it was velocity squared. We now know it's velocity squared is how this is going to change. All right. So we want to kind of move from here to get into molecular kinetic energies. And maybe some of you are looking at this thing and seeing mass times velocity squared, and you're thinking, oh, this is energy. And you're right. That's exactly right. But we're going to do one thing first. We're going to say that we kind of assumed that Vx was the same for all molecules, and that's definitely not true. But what we could have done is basically average them. In general, if I know that an object has a velocity that we call v, that velocity can be broken up using kind of the Pythagorean theorem for 3 dimensions. That if an individual molecule has a velocity that we call v, we can say that the velocity squared is just equal to vx squared plus vy squared plus v squared. And since we're going to be talking about gases where the velocities are basically a random distribution of fast-moving and slow-moving molecules, with most of the molecules being kind of somewhere in between, what we can do is we can basically kind of average this entire equation out so that instead of talking about just the individual velocities, we talk about their average velocities, because this is something that we can describe for the entire system. And then what we can do is we can say that there's no reason why the average x, y, or z velocities should really be any different from one another, that we can basically say that they're all equal to each other. That is to say that Vx average squared should be, there's no reason why it shouldn't be equal to Vy average squared, which should also be equal to Vz average squared. Okay? Which means that we can write V average squared as being equal to 3 times Vx average squared. Because if they're all equal to each other, then this is equal to Vx, this is equal to Vx, you get 3. Which means that Vx average squared, you can see, is going to be equal to V average squared divided by 3. So that's what Vx average is going to be. And what we can do is we can basically say, let's take this and sub it in for Vx. And the reason why, again, is because we assumed originally that all the molecules had the same Vx component, which is kind of not a true assumption. What we could have said, though, is that if we just said, take the average x velocity of the molecules in this region and use that instead, that would have been a perfectly reasonable thing to do, because some of them are going to be faster and some are going to be slower, but using the average velocity is definitely going to be a good way to get a feeling for how it's working. So if we make that change, then our equation is going to become pressure equals N M. And what we're going to do is we're going to replace Vx with V average over 3, basically. So we're going to have V average squared divided by 3 times V. And then the next thing that we're going to do is we're going to say that we know that the kinetic energy, let's multiply the volume too, but we're going to say that the kinetic energy of one molecule is going to be equal to 1/2 mv average squared. Oh, sorry, sorry. This is the average kinetic energy of one molecule. Would be this. And if we do that, and we multiply the volume to the left-hand side, so we multiply volume over here, and we need to replace this in here, so we're going to have to multiply by 2 to do that, so that we don't change anything. So I'll do it in 2 steps. So it'll be 1/2 N, and then I'm going to put in here 1/2 mv average squared. So I didn't change anything. All I did was move volume over here and then pull that out. We end up getting PV is equal to 2 over 3 N times, we call this the translational kinetic energy. So K trans is translational kinetic energy. I mentioned translational because there's also going to be rotational. That's ultimately going to affect this as well. But oh, okay. So actually, I guess what we'll do is, I think I may have mislabeled this. So this is the kinetic energy of one molecule, and if we multiply by the total number of molecules, this actually gives us, here, this is how I want to write this, not as n times this, sorry. Just like this. This would be for the whole gas. So if you take pressure times volume, that's equal to 2/3 of the translational kinetic energy. And there's another way you can write this as well, because we know that PV is also equal to nRT. Right, so that's the other way that you can write this, is that 2/3 of this is the kinetic translational energy is 3/2 times nRT. However you want to write that. Okay, how are we doing on time? We have like 5 minutes left. So let's see if we can get to the last equation here. So how do we get to this equation? Okay, so we look at this relationship here. So translational kinetic energy of the whole gas is defined as N times 1/2 mass of an atom times average velocity squared. So we can say then that the translational kinetic energy divided by N is equal to the kinetic energy of a single atom, or the average kinetic energy of the gas squared. And then we can use one of the other equations to relate this to temperature. So from this equation here, we can replace translational kinetic energy with 3/2 little n RT. Like that. And then we can go, what's N over N? Number of moles divided by number of atoms. Capital N is number of atoms. So if I take number of moles and I divide by number of atoms, what do I get? Maybe I should have said it the other way around. What do you get if you do N over little n? Sorry, flip it. Maybe this will be more obvious. On top is atoms. On bottom is moles. What do you get? You get atoms over moles, which is going to be atoms per mole. What is that? What is the number of atoms per mole? Come on, you all know this for sure. How many atoms are there in a mole? Yeah, which is Avogadro's number, right? Yeah, so this is Avogadro's number, basically. It's one of the relationships from earlier. But anyway, okay, so that means that we can write this as 3RT over 2NA, right? Because it's upside down. And this is equal to 1/2 m v average squared. And now, to introduce you to a new constant, the quantity, if you take R and you divide by Avogadro's number, you get a new constant that's called the Boltzmann constant. So this is KB. You're going to see this show up a lot in this class. So this is called the Boltzmann constant. And it's equal to, I don't know, is it 2.31? Let me see. 1.38. Okay, 1.381 times 10 to the negative 23. Negative 23 because Avogadro's number has a positive 23 in it. Joules per mole Kelvin. Is that it? No. It's joules per molecule Kelvin. It's usually just written as joules per Kelvin, actually. Is usually what it's written as. But anyway, so we call this the Boltzmann constant. And by putting that into this equation, we get to the kind of final form that we want to get to. This was the goal of this whole thing. So you can think of this equation in two different ways. This is the kinetic energy per unit atom. Well, this on the right hand side is the average translational kinetic energy of a gas molecule. This is the mass of a molecule right here. This is the average kinetic energy of a molecule, we'll say. And it's related to just one thing. all the other equations have like pressure and volume in them and all this other stuff, but there's just one thing here. This tells you that the kinetic energy of a molecule is directly proportional to its temperature. And that's the goal of all of this. How is the microscopic velocity related to the macroscopic temperature? And there it is. 3/2 k times T. Super simple. When you think about the energy associated with a gas, when it comes up again in this class, we're immediately going to be thinking 3/2 kT. That's going to be the energy related to that gas. That quantity is going to be what we care about, because that's the average kinetic energy of a molecule. Okay? So, that's it for today. Hope you all have a nice afternoon, and